Today, we're going to dive into one of the most powerful and honestly, one of the most dangerous ideas in all of computation. Recursion. It's a concept that is so elegant, it's almost poetic, but it can also be incredibly tricky. By the end of this, you'll see how it can solve seemingly impossible problems, or, well, create them.
So let's just kick things off with a bit of a mind bender. How do you solve a problem when the problem itself is part of the solution? How do you find your way out of a maze that's constantly redrawing itself? This is the strange, fascinating, and sometimes infinite world where recursion lives.
All right, so what is this powerful idea really? At its heart, recursion is a strategy for solving problems that feels a little like standing between two mirrors and seeing your reflection stretch on forever.
To put it simply, recursion is when you solve a problem by first solving smaller, bite-sized versions of the very same problem. You take a big, messy task and you just keep breaking it down into a tinier and tinier version of itself until it becomes so simple that the answer is just obvious.
And there's a real elegance to it. As computer scientist L. Peter Deutsch famously put it, to iterate is human, to recurse, divine. Iteration, using loops, it's methodical, it's straightforward, it's very human. But recursion? It can feel like you're tapping into a whole other level of problem solving.
But here's the catch. To wield that kind of power, without getting totally lost in that infinite mirror, you have to follow two golden rules. These rules are absolutely non-negotiable. They're the secret to taming infinity. Okay, so every single recursive solution needs two things. First, what we call a reduction step. This just means that every time the function calls itself, it has to be working on a simpler, smaller piece of the puzzle. It has to be getting closer to an answer. And second, and this is the big one, it needs a base case. Think of this as the emergency exit. It's a condition so simple that the function can just give you the answer directly without having to call itself again. Because if you forget that base case, you get this, an infinite loop. It's this endless spiral where your program just calls itself over and over and over, or, at least until it runs out of memory, and the whole thing just crashes spectacularly. The lesson here is pretty simple. You gotta know when to quit.
All right, enough theory. Let's see these rules in action. We'll start with a classic, a textbook example that shows off the elegance of recursion when it's done right, calculating a factorial.
You probably remember this from math class, right? 4 factorial, written as 4 with an exclamation point, is just 4 times 3 times 2 times 1. But look closer. Do you see the smaller problem hiding in plain sight? 4 factorial is really just 4 times 3 factorial.
This fits our two rules absolutely perfectly. The reduction step is defining the factorial of any number n as n times the factorial of n minus 1. See? We're always making the problem a little bit smaller. And the base case is our stopping point. We all know the factorial of 1 is just 1. It's simple, it's clean, it's totally elegant.
So far, so good, right? Recursion seems like this perfect, clever tool. But now, for the twist. We're going to look at another famous sequence that seems like it was made for a recursive solution, but it's hiding a really dangerous flaw.
I'm talking about the Fibonacci sequence. You start with 0 and 1, and then every number after that is just the sum of the two that came before it. It's this beautiful pattern you see all over nature, and its definition is, by its very nature, recursive. And the recursive code for it looks just as beautiful. To find any Fibonacci number, you just find the two numbers before it and add them up. The function calls itself twice. It looks just as clean as our factorial solution. But here's the hidden trap. To calculate, say, Fibonacci of 5, you have to calculate Fibonacci of 4 and 3. Okay, but to get 4, you have to calculate 3 times again. The same work is being done over and over and over.
And this is the price you pay for that hidden flaw. The number of calculations required just explodes. To find the 5th number, it takes 7 additions. The 10th takes 88. But just look at the jump to the 50th. This isn't just growing fast, it's exploding exponentially. It's completely out of control.
To calculate just the 50th Fibonacci number using this method would take roughly 20 billion addition operations. 20 billion. All because the function just mindlessly recalculates the same values again and again, leading to this catastrophic amount of work. So this is the big lesson here. That beautiful, divine solution we wrote? In practice, it's a complete and utter disaster. It's a classic trap where the most elegant-looking path is absolutely the wrong one to take. Sometimes, that beauty has a staggering cost. So is recursion just a beautiful but totally impractical idea? No, not at all. For some of the hardest problems in computer science, it's not just elegant, it is by far the most powerful tool we have. So let's see recursion's redemption with a famous algorithm called merge sort.
Okay, imagine you have a completely scrambled list of numbers that you need to sort. The merge sort strategy is pure recursion. You don't even try to sort the whole thing at once. Nope. First, you just divide the problem. You split the list right in half.
Then you do it again. You recursively call the sort function on each of those two halves, which of course divides them again. And the process just keeps going, relentlessly breaking the problem down into smaller and smaller pieces,
Until you're just left with a bunch of tiny lists containing only one number. And a list of 1 is, by definition, already sorted. And that, right there, that's our base case. We've found the simplest possible version of the problem.
Okay, so now that we've hit rock bottom, we start to build the solution back up. We conquer. We take these tiny sorted lists and we start merging them back into larger sorted lists. And this part is actually really simple. You just look at the first item in each small list and you pick the smaller of the two. You add that to your new, bigger list and you just repeat that until you run out of numbers.
And we just repeat that merging process all the way back up the chain. We merge and merge until what we're left with is our final result, a single perfectly sorted list. This whole divide and conquer strategy is incredibly efficient, and it's just a beautiful example of recursion's true power.
So when you really strip it all down, recursion isn't just some coding trick. It's a whole philosophy for solving problems. You're faced with some huge, impossible task? Don't even try to solve it head-on. Just break it down. Find a smaller version of itself. Keep going until you find the absolute simplest case, your base case. Solve that simple little piece, and then use that small solution to build your way back up.
So that leaves us with one final question. And it's not for a computer, it's for you. What's one impossibly big problem in your world, at work, in your life, that might, just might, be solvable if you stopped trying to tackle the whole thing at once, and instead, you just focused on finding its smallest, simplest version?